Hi everyone, welcome back to the Reading Club. It's an ongoing series where I read papers on mixed integer programming and discuss the key ideas in simple language. So in this episode, we are going to continue discussing the paper Symmetry in ILP by Francois Margot. And this is the third part. If you haven't watched the first two parts, I would at least recommend watch the first part. The link, you can find it in the description. It will make it easier for you to understand the concept that we discuss in this video. So particularly in this video, we are going to discuss about symmetry breaking inequalities. So let's get started. Okay, so there are two types of symmetry breaking inequalities. The first one we are going to look at, it's called dynamic. Right, so these inequalities are actually added during the search tree and they are not really valid for the entire model. So first we are going to look at this, and then we are going to look at static inequalities, which are actually valid for the entire problem all the time. Okay, so why first dynamic? Because that's how the order is in the paper, and it's like very little bit is given for this section, right? So it's not much to cover here, only a high level overview is given, so that's what I'm going to do. Okay, so let's see how that works. So during the search tree, let's say we have certain variables that are fixed to some values. Okay, so let's say we have x1, x2 and x3. There are three variables. This one is fixed to 5, this one is fixed to 7, and this one is, let's say, fixed to 11. And we are at the middle of the search tree, and we are somewhere in the node, and we still have a lot to explore. Okay, there is a big part of search tree that we still have to explore. So what we can do is, if we, let's say we have some symmetry group known to us, that is, this is the symmetry group, and let's take a particular permutation in that symmetry group, right? So the symmetries, as I explained in the previous part, they are actually represented as permutations of indices. So let's say this permutation is say 4, 5, 6, 1, 2, 3. That basically means that 1 is symmetric to 4, 2 is symmetric to 5, 3 is symmetric to 6, and 4 is to 1, 5 is to 2, and 6 is to 3, right? So this is how the symmetries work. So 1 is symmetric to 4. That's something that we know, right? So what we can do here is we can add inequalities that prevent certain types of assignments for the unfixed variables, right? So what are the unfixed variables here? Are 4, 5, 6. So particularly what it prevents is this one, x4, x5 and x6. So it prevents this assignment particularly. x4 is assigned 5, x5 is assigned 7, and x6 is assigned 11. Okay, so this particular assignment we can prevent. Like, so we can add inequality that removes this particular assignment for the rest of the search tree, and that is valid. So this inequality will not be valid at the beginning of the search tree, but since we are here at this node, so under this node where x1 is fixed to 5, x2 is fixed to 7, and x3 is fixed to 11, because they are symmetric to 4, 5 and 6, we can say that 4, 5 and 6 should not take this exactly the same triplet 5, 7 and 11 values, right? So this basically also assumes that all symmetric variables take different values. In all feasible solutions, or at least in optimal solutions, right? So since we have one solution where x1 is 5, x2 is 7, and x3 is 11, and the way the symmetries work is basically it's basically based on the solution space, right? So if we can call x1 and x4 as symmetric if there is a solution where we can say that x4 is taking value 5, 5 is taking 7, and 6 is taking 11, and there is another assignment for 1, 2, 3 for this solution, right? So if this is this assignment is allowed, then x1, x2, x3 takes, there is a feasible solutions where x1, x2, x3 take some other values, and we still find a feasible solution. So if this assumption is true, and if we have some fixed variables, then we can add inequalities that to prevent this kind of assignment, and that's basically the main idea behind dynamic symmetry breaking inequalities. Okay, so now we are going to focus on static symmetry breaking inequalities. These inequalities are valid for the entire problem, and it doesn't matter no matter where we are in the search space. Okay, so let's see what we are trying to do here. So let's say we have a two-dimensional polyhedron, something like this, and we have some points, feasible points inside it. Let me draw some feasible points. Okay, so in general what we end up doing is that we end up exploring this entire polyhedron, all these feasible points, and then we select one of them as optimal, and that's how we do our search. But if our problem is kind of symmetric, then we want to exploit the symmetries in this, right? So we say that, you know what, I don't want to explore the entire problem, I just want to explore this part of the problem, and if I explore just this small part of this problem, then it is basically equivalent to exploring entire search space, because this the other points are roughly symmetric to something in here. Okay, so that's the key idea, right? So we have our symmetries represented as permutation, just to remind you. So it's a permutation of this 1 to n indices. We have n variables, and this one permutation is called like one symmetric permutation, and there is a group of such symmetric permutations. It's called this symmetric group, right? So we are going to define a fundamental region for this symmetric group. Okay, so fundamental region. This fundamental region is for the symmetric group, and it's not for the problem, it's for the entire group. Okay, so it actually can basically lie outside of part of it can also be outside of this search space, but so the idea is that we explore the search space which is inside this polyhedron, and it's inside this fundamental region, both. So intersection of these two, that's what we end up exploring. And so first property that it should have is that it should be small, obviously, because if it is too large, then it doesn't make sense, right? Because then we'll end up exploring this entire polyhedron anyways. So it has to be small, or at least not too large. That's one property. And second is that it must contain at least one optimal solution, right? So that's why we can justify that we only want to explore this part. If the optimal solution, all optimal solutions are outside of this region, then we still have to explore some other parts of this search space, and that's what we don't want to do. We only want to explore this part. So, and at least one optimal solution should be inside this area. Okay, so in the paper they have defined that this is a closed set in Rn. Okay, so I don't know why exactly this closeness is needed, but we'll see. So for those of you who don't know any topology, this closeness is closed set basically means that it includes all of its boundary points. Okay, but at least we understand these two things that it needs to have. So how do we define this kind of region? So it should have two properties. The first property is that if I take an image of any point and I permute it using this permutation, right? So this is a permutation of n indices, and this is every point is basically a point in Rn, right? So it has n indexes. So if you permute these indexes using this permutation, then it should map something out of this region, right? So anything points inside, then it should map to something that is outside under G, right? So this point might map to this one, this point might map to this one, this point might map to this one, something like that, right? So that is G of any point inside of F, interior of F, right? Should be, if I take an intersection with the interior of F, then it should be phi. Okay, it should be empty. So again, like I don't know why this interior points are needed, why not the entire region? I haven't understood that part, but that's how it is defined. So the key idea is that it actually ensures that these sets are small. Why? Because and so this should happen for all G in G, all the symmetric groups except the identity permutation, right? So the identity permutation will basically map any point to itself, and that's why it's not outside of the interior region of this fundamental region. So other than that, any permutation should map any point inside to the point outside. So why it is small, or rather not too large? It's because if it is too large, then I have many groups over here, right? So if it is too large, then what will happen is that under different symmetric groups, it might not, if it is too large, then it might end up mapping some point to its something that is inside it, right? So that's something that we don't want to happen. So if it is small enough, then it is easier to ensure that every point maps to something that is outside of it, right? So if it is too large, then we might end up mapping a point to its something that is inside. Okay, so that's basically something that ensures that it is small, like not super small, but at least not too large as well. Okay, and there is another property. It's called it goes like this: if I take the union of applying G to the points in F, right? And if I take all such permutations G in my group, so these are all my symmetric groups, and I take an image of this fundamental region under G, and I take a union of all such G's, okay? Right? So again, recall that every image for any point inside it will map to something that is outside. So what this property is saying, that if I take the union of all the symmetric permutations, and if I take the image of this, then this should map to the entire Rn, not just this polyhedron, but the entire the search space or vector space Rn. Okay, so this basically ensures the second property. Why? So again, like this, G's are symmetric groups, right? And these symmetries are defined based on the solution. So let's say all my permutations are outside, all my optimal solutions are outside, right? So let's say these are the only 4 optimal solutions for this problem, and none of them are inside this, then it doesn't make sense. Why? Because this property is holding. That means there has to be some permutation G that covers this point, like this optimal point, and that should its pre-image should lie inside this fundamental region. So it has to map something to, let's say, this point to this point. Okay, so now since G is my symmetric group, right, it defines the symmetry, the objective value of this point and this point has to be the same, right? So that's how we have defined the symmetric groups. So if you haven't seen that, then you have to like watch the first part, in which we have basically defined how these symmetries are represented, the symmetric permutations, right? So if we basically permute these values of this variable, then the objective does not change, and that the new solution under the permutation still remains feasible, right? So that's how we have defined the symmetric groups. And so at least some point should be inside this fundamental region, right? So, and because this is feasible, this also has to be feasible, and it basically has to have the same optimal value, and so it has to contain at least one optimal solution. So if it satisfies this property, then it has to contain at least one optimal solution. Okay, so these are the 2 properties that we need for defining this fundamental region. So if we have this fundamental region, somehow if we have figured out a fundamental region for this symmetric group, then we can restrict our search to this small area, and it will be like we can like solve this problem much faster if we don't if we explore this small area only, instead of exploring the entire search space, right? So that's the idea behind the fundamental region. Okay, so now we have defined what fundamental region is, and we also know that searching only over this fundamental region where it intersects the polyhedron is sufficient. So now the goal is that how do we find it, right? So we have, let's say, a symmetric group G, right? So it has a bunch of permutations which are basically representing my symmetries. Then how do we find the fundamental region for that? So it turns out there is a theorem. It says that we need to find one point, x bar. This point should be in Rn. Okay, it does not need to be a feasible point in my polyhedron. It can be any point, as long as it satisfies this following property, right? So if I take any permutation G from this group G, and if I take the image of x bar, if I permute the indices of this point, then it should not be equal to the point itself, x bar. And this should be true for all G which are in G and that are not identity permutations. Okay, so just to validate, some points don't satisfy this property. So for example, if I have a point in Rn which are all zeros, let's say like this, then this point does not hold this property. Right? Because no matter how I permute the indices of these zeros, it will all remain 0, and g of x bar will be equal to x bar for all of them. So that's not valid. In fact, none of those 2 points can be seen. None of the coordinates can be seen, right? So let's say if we have some point, let's say it has just these 2 zeros and other indices are different, then I can have a permutation which permutes 1 to 2 and 2 to 1, and under those permutations it will map to itself. Again, like that has to be a permutation inside my symmetric group, right? So in the case where 1 and 2 are symmetric, then this is not a valid point also, right? So these points are not valid. Okay, so what about that? Let's say we have found a point which is inside Rn, may or may not be feasible, and under any permutation that are symmetric, its image is not itself. Okay, now what? So if we have this inequalities, g of x bar minus x bar, so this is a constant now. Okay, this dot product x is less than equal to 0. This is one linear inequality for one g, right? And if we add it for all g, then this basically defines a fundamental region, right? So this for all g, if I add all of these inequalities, then this is a fundamental region. So this x belongs to Rn, where x satisfies this inequalities, then it's a fundamental region. There is a theorem like that. The proof is not given in the paper, so I'm not going to discuss it again. But this is a theorem. Okay, so if we have the symmetric group, then we know how to find this fundamental region by using a set of inequalities, and these are all static inequalities. All of them will break symmetries, right? So it's a very small region and it contains the optimal solution and everything. So that's the goal. We have found the fundamental region. Now there are some tweaks to this. So first of all, it's kind of sometimes there can be like too many G's, like too many symmetric permutations. So this number of inequalities can be too large, and that can be sometimes an issue, right? So if we have a fundamental region but that is too large to describe, right, in terms of inequalities, then it's of no use, right? So there are another properties that are like that, so that are defined like this. So if we can apparently drop this requirement where g of x bar is not equal to x bar for all g not equal to I, and or we can also drop this requirement, like we can only use a subset of these inequalities which are not, like, basically not all permutations under our symmetric group G, but we only like a small subset of this permutation. In that case, what we get is not a fundamental region, but let's say a region f prime, let's call it. Then also kind of it is sufficient to, let's say this is my region f prime. This is, let's say, my fundamental region. What I get by dropping this two or one or two of these requirements is that I get a bigger region f prime, right? So that is also kind of sufficient, right? So if we only explore inside this f prime region, that where it intersects the polyhedron, that's also kind of sufficient. Like it will also contain at least one optimal solution, right? So again, like the two properties that we cared about, right? So one of them was, first, it should be small, and second, it should contain optimal solution. So only this first one might be broken under if we drop this one and this requirement. But this property where it contains the optimal solution, this remains valid even if we drop those things, right? So this is now we have an easy way of finding at least some region which is defined by this linear static inequalities, which kind of removes a big part of our search space. Okay, so that's a good thing. Now let's take a look at an example. Okay, so there are many examples given in that paper, but I'm only going to describe one of them, which is kind of the simplest example, right? So we have, let's say, n variables which are between 0 and k. Okay, so let's say x belongs to Rn, and let's say all of them are symmetric to each other, and we want to break this symmetry. So right, so one way of breaking symmetry is that if we add this inequalities, then the symmetries are broken, right? So otherwise, let's say if we have a solution 1, 3, 5, 7, then a solution which is 7, 3, 5, 1 is also feasible, 5, 7, 3, 1 is also feasible. But if I add this inequalities, then all of these solutions are gone, right? So all the symmetries are gone. So apparently these inequalities can be achieved from or static inequalities based on the fundamental reason that we just discussed in this video. Okay, so let's see how that works. Okay, so first of all, my symmetry group is basically set of all permutations because all variables are symmetric to each other, right? And we need first of all a point x bar, right? So the way I'm going to define x bar is something like this. Its ith index is I, right? So 3, 4, and so on and so forth up to n. So this is my point, which may or may not be a feasible point again. So the point is that doesn't matter how I permute it, its image will be different from itself. That's the property that I needed, and that's the property that I'm keeping. Okay, so let's see an example where n equal to 3, and let's say my x bar is simply just 1, 2, 3, and let's say under some permutations my g of x bar looks like say 2, 3, 1. Right, so this is one permutation where I have permuted the indices, and that's how it looks like. Okay, so what would my static inequality look like, which was basically g of x bar minus x bar. These were my coefficients of x should be less than equal to 0, right? So 2 minus 1, that is 1, so coefficient of x1 is 1. 3 minus 2 is 1, so coefficient of x2 is 1. And 1 minus 3 is minus 2, so minus 2x3. This is less than equal to 0, right? So again, like this basically dominates this inequalities, right? So it can be derived from this, where it basically says that x1 is less than equal to x3 and x2 is less than equal to x3, right? If we just add up these two inequalities, then we get this inequality. And that's for one permutation group, or one permutation, this one, right? So we have to do it for a couple of other permutations, then we might even obtain all three of them, right? So where we also obtain x1 is less than equal to x2, right? So that's the idea, right? So again, like all of these inequalities can be obtained by using this fundamental region properties, and static inequalities we define using that. So there are so many other examples that I'm not really going to discuss, but so basically the idea is that there are a lot of cases where we can find out the symmetric groups, and we can find out a bunch of static inequalities which will a procedure to find static inequalities for doesn't matter what the symmetric group is, right? So that's a nice thing that we have, right? So in this video we saw dynamic symmetry breaking inequalities and static symmetry breaking inequalities, and for that we defined a fundamental region. And using this fundamental region, we figured out a small part of it can also be used for static inequalities. So that's the main idea behind doing all this symmetric work. So once we have figured out symmetric groups, again, like those things we discussed in the first part, where we can basically find out the symmetric groups using graph automorphism basically. And once we have found the symmetric groups, there are ways in which we can find these fundamental regions, and based on that we can find this static inequalities, right? So this fundamental region is apparently defined by linear inequalities, which is another nice property to have. The problem with this fundamental region is that sometimes we have to find out a point x bar which is kind of weird, and if we are in a large space, then the coefficient that we obtain by this kind of operation, g of x bar minus x bar, they can vary in magnitude, right? So some coefficient might be too large, some coefficient might be too small, and that can cause issues in basically numerical issues when we are solving the integer linear program using simplex methods. Okay, so typically like this kind of static inequalities, it's kind of easier to add them in constraint programming rather in the simplex based branch and bound search. So that's something that mainly because of this numerical instability related reasons, right? So these inequalities have some weird properties and they are not all of them facet defining for the fundamental region. So again, some of them might be completely dropped, we just don't know which one to drop, and they might be redundant, might cause numerical issues, but they are at least breaking all the symmetries, right? So we at least have a procedure to break symmetries now. So I hope you learned something new on this, right? So if you do, then don't forget to hit the like button and don't forget to subscribe if you are new here. So see you in the next part where we discuss more concept in symmetry.